Hello, good evening. How are you guys? Hopefully, you are doing good. Okay, so in the previous video for Unit 6, we started looking at LAN technologies as well as network topologies. And we'll just continue in this part 2 of our video. We looked at the topologies, the ring, the star, as well as the bus technology topology. So we also looked at the advantages as well as disadvantages. Today we'll continue. We'll start from LAN technologies and what they are. So our example bus network is Ethernet. So Ethernet is one of the LAN technologies. Ethernet is a well-known and widely used network topology that employs bus topology. You remember the bus topology is where you have one line and multiple nodes or computers connected to it. So Ethernet is a traditional technology for connecting wide area networks. So like the way we have computer labs, those most of our computer labs are wired. So those we are referring to them as wired networks, and since they are classified as local area networks, those can be called wired local area networks. Okay, so Ethernet is the traditional technology for connecting wired local area networks, enabling devices to communicate with each other via a protocol, which is basically a set of rules that help in network communication. Okay. The history of Ethernet. So Ethernet was invented at Xerox Corporations at the Palo Alto RC in the early 1970s. Digital Equipment Corporation, ITEL Corporation, and then Xerox later cooperated to devise a production standard. Informally, it was called DIX Ethernet for the initials of the three companies that came together to work on this particular technology. The Institute of Electrical and Electronics Engineers, which is IEEE, now controls this Ethernet standard. In the original form, an Ethernet consisted of a single coaxial cable that was called the ether. The term segment to refer to the Ethernet coaxial. A given Ethernet segment is limited to about 500 meters in length and requires a minimum of separation of 3 meters between each pair. Ethernet comes in a number of versions. The original Ethernet operated at 10 megabits per second. A later version known as Fast Ethernet operated at 100 megabytes. And then now we have what we call Gigabyte Ethernet, which operates at 100 MB or 1 GB per second. The history is not something that should bother you much, and you don't expect me to ask any questions in any test or an exam on the history of Ethernet. I may ask you questions on Ethernet transmission and Manchester encoding. If you are a Manchester fan, you need to pay attention because this Manchester encoding is something that I usually ask in the exams. If you remember, I earlier brought an encoding scheme in the other paper, which was RIS 232. Okay, so apart from RIS 232, we also have some other encoding schemes, and one of them is the Manchester encoding. So the Ethernet standard specifies all details, including the format of flames that computers send across the ether. The ether, we are just referring to that cable that is used in this network. The voltage to be used and the method to be used to modulate the signal are all part of this standard. So the Ethernet standard specifies the flames are sent using an encoding scheme called Manchester encoding. Technically, the hardware is said to be edge triggered, and the changes are known as rising or falling edges. Manchester encoding uses rising and falling edges to encode data. What do we mean? Let me just scroll. So they are calling these rising, like if it goes up, it's a rising edge. If it comes down, it's a falling edge. So Manchester encoding uses a rising edge as well as a falling edge to represent your data. So a 1 is representing by a rising edge, and then a 0 is represented by a falling edge. You remember in RIS 232, we are using positive 5 to positive 15 to represent a 0, negative 5 to negative 15 to represent a 1. So in this scheme, you use the rising edge to represent a 1 and the falling edge to represent a 0. Another rising edge to represent a 1, a falling edge to represent a 0, just like that. Okay. So Manchester encoding uses rising and falling edges to encode data. Transmit a falling edge to encode a 0, like I've said, and the rising edge to encode a 1. The figure below, which is figure 6, illustrates how the Manchester encoding is displayed. Okay. So to make sense of the incoming signal, a receiver must know exactly when each time slot begins and ends. If you've noticed with the Manchester encoding, there are time slots there. So these time slots are representing when it starts and when it ends, when it starts and when it ends, when it starts and when it ends. Okay. So a preamble consists of 64 alternating ones and zeros, but don't really dwell much on that. The receiving hardware uses preamble to synchronize its notion of time slots with arrival signals. Once the preamble has been processed, the receiver can correctly identify successive bits. In summary, Manchester encoding uses 2 intervals to represent a bit period. In summary, Manchester encoding uses 2 intervals to represent a bit period. That is from low to high representing a 1, and from high to low to represent a 0. What do we mean? So we are saying in summary, this is, let me even highlight. In summary, Manchester encoding uses two time intervals to represent a bit period. So 2 time intervals, if you've seen these dots here are representing a time interval. Okay, so there is this time interval there to there to there and to there. This is so this particular one here is representing 2 parts of this of the 1. Okay, so 1 here is representing 2 halves, 2 time intervals. So we are saying in summary, Manchester encoding uses 2 intervals to represent a bit. That is from low to high to represent a 1. So when you want to draw a 1, you have to start from low. The starting, if you can see the blue color there, starts from low and then goes to high. So 2 time intervals. The first one, we are saying, let me just highlight what we are saying here. To represent a 1, we are saying you move from low, the blue starts there, you move half of the 1, half distance of the 1, from a low to a high, up to there. You finish. So the dots there are representing time interval number 1. The dots there are representing time interval number 2. The dots there are representing time interval number 3. So if you want to represent a 1, the one that is on top there, you have to move from low to high up to where the time interval ends. If you want to represent a 0, you have to move from high to a low up to where the time interval for 2 ends there. We are trying to represent a 1 there. We are moving from low to high, up to where the time interval ends. A 0 from high to low, up to where the time interval ends. We want to represent a 1. So a 1, we won't just go up and go like this. We are saying a 1 moves from a low up to a high there. We want to represent again a 1 if you've noticed. So a 1, we are saying a 1 starts from a low to a high. So since we are already on a 1 there, we need to come down so that we start from a low to a 1. Hopefully you've noticed. For a 1, we are saying you have to start from a low to a high there. And since the next figure we are representing is a 1, you have to start from a low. So we'll go down where this time interval ends. You start from a low up to a high. Okay, just like that. So this is telling us, say, from a low to a high, we represent a 1. And from a high to a low, we represent a 0. So I may ask you in an exam to say, how do you represent a 1 in Manchester encoding? So you represent a 1 in Manchester encoding by drawing from a low to a high. And if you want to represent a 0, you are drawing from a high to a low. This is very important. The time intervals as well, you need to draw them. You need to do these dotted lines so that you specify this is 1, this is 2, this is 3, this is 4, until the end, depending on how many bits you are asked to represent using Manchester encoding. Okay, let's move on. But if you have questions on that, you can easily ask. I should be able to clarify on the day that you guys will give me for us to just go through most of these issues. So figure 7 illustrates how data flows across an Ethernet. A signal propagates from the sending computer to both ends of the shared cable. Sharing in LAN does not mean that multiple frames are being sent at the same time. Instead, the sending computer has exclusive use of the entire cable during the transmission of a given frame. Other computers must wait. That is, after one computer completes transmitting one frame, the shared cable becomes available to another. So this is how Ethernet is implemented, using a bus topology like we said. So this is one common cable. So as computer 1 is trying to send, no other computer will be allowed to send, not until it sends its frame. Then another computer will be allowed to send, just like that. So when one computer is sending, only one computer at a time is able to send. But you discover to say there will be a point where none of them are sending. So as we go on in this handout, I'll guide you through what we call carrier sense multiple access. So before this one sends, before any of these computers sends, it has to check what is on the cable. Is someone sending? If no one is sending, then it will send. But imagine where this computer checks, there's nothing. At the same time, this computer is checking, there's nothing, and then they both send. Then there will be a collision, right? So this one had to check, okay, there's nothing on the Ethernet. This one as well checks, there's nothing on the Ethernet. So as they try to send, there will be a collision because they both thought no one is sending and they both had to start the sending process. So this is where we come to what is known as carrier sense on multiple access network. This is a multiple access network where multiple computers are accessing a network. So carrier sense on multiple access networks. An Ethernet does not have a centralized controller. If you've seen in this Ethernet, there's no controller like we had in a star network where we have a hub. Every computer can communicate at any given time. All computers attached to an Ethernet participate in a distributed coordination scheme. And this scheme is called carrier sense multiple access. The scheme uses electrical activity on the cable to determine a status. When no computer is sending a frame, the other does not, when no computer is sending a frame, the ether does not contain electrical signals. So to determine whether a cable is currently being used, a computer can check for a carrier. So a computer will check, is there anything that is being sent? If there is nothing that is being sent on the network, then it will send. So if no carrier is present, the computer can now start transmitting a frame. If a carrier or if there is a signal on the or present on the network, the computer will wait for the sender to finish before proceeding. Checking for the carrier wave is what is called the carrier sense. So each computer will sense, will check what is on the cable or what is on the ether channel. Is there something? So there what it's doing is it's trying to sense. Okay. Collision detection and backoff with carrier sense, with carrier sense, multiple access, and collision detection. We've said it's possible two nodes can actually detect that there is nothing on the network and they both start sending at the same time. In the end, they collide, right? Okay. So carrier sense multiple access allows a host to determine whether a shared cable is already in use by another cable. It also prevents from interrupting an ongoing transmission. However, carrier sense cannot prevent all possible conflicts. For example, two computers can sense at the same time and find that the cable is free, just what I'm talking about. They then start transmitting data simultaneously. This causes an interference, that is, mixture of the two signals. The interference or mixture of the two signals is what we call a collision. This collision produces a garbled transmission and prevents either of the two frames from being received correctly. To ensure that no other transmits simultaneously, the sender should monitor signals on the cable. If the signal differs from the signal that the station is sending, it means that a collision has occurred. So in as much as a computer is sending on this the network, it also needs to keep monitoring. Is it the signal that I'm getting on the network, is it what I sent? So if there is a collision, which means the two signals sent by machine A and machine B will collide, and then they'll form a different signal. So the sending computer will be able to detect to say there has been a collision. So to guarantee that a collision that a collision has time to reach all stations before they stop transmitting, we need to limit on the maximum cable length and the maximum frame size. Whenever a collision is detected, a sending station immediately stops transmitting. So monitoring a cable during transmission is what is known as collision detection. And the Ethernet mechanism that does that is called CSMA/CD, carrier sense multiple access with collision detection. Carrier sense multiple access with collision detection does more than merely detect collision. It also helps to recover from them. So after a collision occurs, a computer must wait for a cable to become idle again before transmitting a flame. If a computer begins to transmit as soon as the ether becomes idle, another collision will occur. To avoid multiple collisions, each computer should delay a collision, should delay after a collision before attempting to retransmit. A maximum delay period denoted by the letter D forces each computer to choose a random delay less than D. When a computer chooses a delay of random, it will select a value that differs from any of the values chosen by the other computers. The computer that chooses the smallest delay will proceed to send the flames and the network will return to normal operation. If two or more computers happen to choose nearly the same amount of delay after a collision, then they will both begin to transmit at nearly the same time, producing a second collision. To avoid such a thing or such a sequence of collisions, stations double the range after the collision. Okay, I may not really ask you on this, but you can just read more so that you get to understand. So this as well I just want you to read on, but don't expect me to ask you questions on the wireless LAN 802.11b technology. Just read on so that you can have a more understanding, but don't expect me to bring any questions from there. As well as another example of bus network, which is local talk. Just read on that, but don't expect me to bring any questions from that. So with that, guys, this is where I conclude our handout 6. So handout 6, mostly you need to read on what a LAN is, what is a network topology. You need to read on direct point-to-point communication. You need to read on shared communication channels. You also need to read on significance of LANs and locality, but here as well, I just need you to have a concept. I may not ask anything in any of your tests or the exam. You need to read on the LAN technologies, which is the star, the bus, as well as the ring topology. Advantages, disadvantages, get to read on that. I will surely ask questions on that. Apart from that, also read on what we are just from looking at, which is an example of a LAN technology, which is called Ethernet. Read on Ethernet, not the history. Like I said, I won't ask anything on the history. I'll ask mostly on the Manchester encoding scheme. Apart from that, read on carrier sense on multiple access. Okay, and that should be it, guys. So for now, that's our end for handout 6. Expect some more videos for handout 7 up to 10. We'll be doing a marathon, so hopefully you won't be left behind. Have a blessed day, guys, and remember to just send me something in case you have a query, and I'll address it. Thank you very much.